Everybody wanted to spend a little bit of time going over question 21.30 in Brown-Lemay Burston. And so all we're asked to do is fill in the missing particle that's given by the nuclear reactions. Now, these are fun for me. I like doing these. It's like a piece of finding puzzle pieces. Now, I would definitely keep out your periodic table in front of you. It helps out a little bit, but let's get started. So here for part A, remember this side has to equal this side. So this is 9, and this is 1. So the atomic number has to be 8, which I know is oxygen. I can write that already. Okay, and then 14 and 4 is 18, but this is 1, so this is going to be 17. So 17 plus 1 is 18, 8 plus 1 is 9, everything is good. Okay, so now for B, this is an interesting little thing. I don't think, for me, it matters where the electron comes from, but this is what we call electron capture. I'm not asking you to necessarily recognize the process that's going on here, okay? But I will say that, electrons can come from anywhere for electron capture. That's why we use this, the symbol of an electron here, okay? But let's take a look here. Let's do this. So what is it going to form? Potassium undergoes electron capture. So that is going to, for B, okay, 40 plus 0, okay, equals, so this is going to go to 40. And now it's going to capture an electron, 19 plus a negative 1. Be careful. A lot of students miss that with the negative sign there. So that's 18. 19 plus a negative 1 is 18. And then that's going to be argon. Okay, so now here we have something in part C where we're going to be at the beginning. It doesn't change our thought process. Remember, the mass numbers have to equal, and so do the mass and the blah, blah, blah. It's good for me to speak here, and so do the atomic numbers. So the mass number here is 31, and this is 4. Okay, so this has to be a 27. And this is 15, but this is 2, so that's 13. So element number 13 is aluminum. Okay, then we do the same thing here with question D, same thought process. Okay, now we have a coefficient to worry about. That means there are 2 of these guys, and this is a neutron. So this is neutron capture. Okay, again, I'm not concerned necessarily that you know what the process is, but that's what we're going to call it, neutron capture. Okay, and so again, this side has to equal this side. Okay, so this is going to be 58 plus 2 times 1 is 60. Well, that's 60, so that's 0 at the top for this one. And then 26 plus 2 times 0 is 26, so it's 27, so this has to be negative 1. That symbol then is going to be a beta. It's a nuclear equation, so I prefer, because it's a nuclear equation, that it's releasing a beta particle. Okay, and then E, let's do the last one. Okay, so now there's more junk here. There's 5 things to worry about, but the process is still the same. Okay, it may be longer, but it's definitely not harder. Okay, so this is 235 plus 1 is 236. Okay, so here's 135 plus 2 is 237, so that means that this has to have a mass of of 99. Okay, and then 92 plus 0 is 92, so that's 54 plus 2 times 0 is 0, so 92, 54, that must mean that this bottom number is 38. Make sure I did my math right. 38, 2, carry 1, 92. Okay, great. And so we look at the periodic table for what 38 is, and that's strontium, which is actually a common, what do they call it? A common fission product, strontium 99. Common for whatever that means when we do our nuclear chemistry in our backyard. But you get the idea. So this is a fission process where we bombard uranium with a neutron, and when it does that, it splits apart, gives off 2 more neutrons. So now we have xenon and strontium. Now the funny thing is those 2 neutrons can then create 2 more reactions between a uranium, which only needs 1, which you can create. And so that is actually an interesting chain reaction that happens when we do in nuclear chemistry. But enough of that here. Okay. So I hope this clears up balancing nuclear reactions. Have a great day.